IGCSE Computer Science, Syllabus Statement 2.1.1d, work out the purpose of a given algorithm. So in the last video, we looked at trace tables for like one algorithm, and it was a little bit rushed, I thought, but hopefully you have an understanding. But you know, if you're still struggling, well, there's this video. Now, although in this video we're looking at working out the purpose of a given algorithm, well, we need to first fill in a trace table in order to actually do this. So that's what we're going to do. Now, we're not going to use the same algorithm as we used last time, because that would be stupid. So we're going to use a different algorithm. So this one I got from the October paper 2015. And this algorithm looks pretty, well, I mean, it looks okay. I mean, it's a little bit tricky, but, you know, it's quite straightforward if you use a trace table, I'd say. But that's just my opinion. So, in case you don't know what the div and mod functions do, div gives the integer revision of a result. I meant to say the integer result of a division, and mod gives the remainder of a division. So what this means is 10 div 3 is 3, because 3 goes into 10 3 times, so the remainder is ignored, and 10 mod 3 gives 1, which is the remainder. So 10 divided by 3 is 3 remainder 1, so 1 is returned. So hopefully you could, you'll see what this does. Just pretty much gets the division and the remainder. Both of these. So we got, you get the point. So let's trace this. Our input data is going to be 12, because that's one of the values on the mark scheme. So let's set up our trace table, and we can start tracing. So start, position, I guess, position equals 1, new equals 0, input x, so we input 12, and we can start with the real stuff. T1 equals x div 2. So x divided by 2 gives 6, and x mod 2 gives 0. You can see how this works, because this is an even number. We all know that 2 can go into all even numbers without a remainder. Next we have new equals new plus t2 times position. Now be careful here, because it says new plus t2 times position. And remember that we multiply first and then add. So t2 times position is 0, and new is 0, so the value will be 0. Now hang on a second. You might be wondering, didn't you say that we record the result in the trace table whenever the value changed? Well, technically the value did change, because we assigned it a new value, but the value is just happens to be the same as the old value. So although the value didn't really change, it did change in a way, because we have this old 0 here and this new 0 here. So that's how it works, in case you were wondering. Then position equals position times 10, so 1 times 10 makes 10. Is t1 higher than or equal to 2? Yes. X equals t1, so x is 6. t1 equals x div 2, simple, 3. t2 equals x mod 2, that also gives 0. New equals new plus t2 times position, so t2 times position makes 0, new is 0, so 0 plus 0 makes another 0. Position equals position times 10, so that makes 100. Is t1 higher than or equal to 2? Yes. X equals t1. t1 equals x div 2. Now here's the little odd we have an odd number here. So here we have 2 going into 3 once, and t2 is x mod 2. So 3 mod 2 gives 1. So we have 1 remainder 1. New equals new plus t2 times position. Now we actually have a value for t2. So we have 100 times 1, which gives 100, plus 0. So new is 100. Position equals position times 10, that gives 1,000. Is t1 higher than or equal to 2? Nope. So new equals new plus t1 times position. So t1 times position is 1 times 1,000, which gives 1,000. 1,000 plus 100 is 1,100. And we output new, which is 1,100. So there, we've looked at a trace table. Now, see if you can work out the purpose of the trace table. Now, what they mean by purpose is you're basically saying what it does. So what does this program actually do? Now, here's how you do it. You look at the input and look at the output and see how they are similar. See what you're trying to see. What is this trying to do? And you may also get a hint by looking at the variable names. What's the purpose of making this position? What's the purpose of making this new? If you haven't figured it out yet, then we can look at another one. Another one. So here our input data is going to be 45, a little bit bigger. Actually, quite a lot bigger. Anyway, set up our trace table. Position 1, new 0, input 45. T1 equals x div 2. It's 22. And a remainder of 1. New equals new plus t2 times position. T2 times 1 makes 1. And position, of course, becomes 10. Is t1 higher than or equal to 2? Yep, definitely. X is t1. And t1, which is, x is 22. So 22 divided by 2 gives 11. Remainder 0. So t2 is 0 because x mod 2, 22 mod 2 is 0. So remainder of 0. New equals new plus t2 times position. So t2 times 10, 0 times 10 rather, is 0 plus new, so that's 1. Position equals position times 10, that's 100. T1 is still higher than or equal to 2. So x is t1. T1 is x divided by 2. So T1 is 11 divided by 2, which is 5, with a remainder of 1. New equals new plus t. You know, this is I'm starting to sound like a broken record here. New will be 101 because 1 times 100 plus 1 makes 101. And position, of course, becomes 1,000. Is T1 higher than or equal to 2? No, not yet. X is 5. Then T1 becomes 2 because 5 divided by 2 gives 2 with a remainder of 1. 1 times 1,000 plus 101 gives 1,101, and position becomes 10,000. Is T1 higher than or equal to 2? Yes, it still is. So X is 2. And then T1 is 2 divided by 2, which is 1, with a remainder of 0. New is the same. Position is 100,000. And finally, T1 is not higher than or equal to 2. So new equals new plus 1 times 100,000. And that gives 101,101. So then we output that. Have you still haven't figured it out? Well, let's look at this. So here's our original one with the input data 12. Now, what do you notice about both this and this, both 12 and 45. What do you notice about the outputs? Well, they're all ones and zeros. Ones and zeros. So what can that mean? Well, we remember from the very first topic that binary consists of ones and zeros. So could this algorithm convert a decimal number into binary? Well, let's check that. 12 outputs 1100. So it's 8 plus 4. 8, 9, 10, 11, 12. So it works for 12. Well, does it work for 45? Well, let's give it a shot. We have 32 plus 8, and that gives 40. And then 40 plus 4 gives 44, plus 1 gives 45. So yes, the purpose of this algorithm is it converts a decimal number into binary. And that's pretty much it. Now the reason why I wanted to get into this in depth is because I sort of struggled with this kind of stuff, and I still kind of do. Because the first paper that first past paper that I tried, there was one where the purpose was I think a check digit calculator or something like that. And I was just like, okay, I did the trace table, all fine, it's all good. And then it said, state the purpose of this flowchart. I'm like, what? What is this? What is this supposed to be? Like, well, and then I looked at the mark scheme, and then it's just like, oh, it does this the check digit, whatever. I'm just like, oh, well, I feel really stupid now. But yeah, hopefully the tips that I've provided will help. Again, just think about the input and output, why you would get this output with this input, and also look at the variable names. Why would they name this position? Why would they name this? And so on. So yeah, thanks for watching. Hopefully you learned something. And the next video is going to be, if I can remember, I can't remember, sorry. But you'll find out.